Good afternoon. This is Ed Salzberg. I'm the Managing Director of the Security and Sustainability Forum, and I welcome you to the third webinar in our Future of Sustainable Transportation Fuels series. This one is on recycling CO2 to liquid hydrocarbon fuels. We're co-hosting this series with Lightspeed Solutions, an initiative of Lightworks at Arizona State University. The series is led by Ellen Stechel, Director of Lightspeed Solutions and Deputy Director of Lightworks. Ellen's a leading researcher and policy analyst in the sustainable fuels field. The forum was born out of Ellen's passion to create an inclusive forum to engage sustainable fuel stakeholders in conversations that can lead to a low-carbon, sustainable future. Ellen encourages you to keep the conversation going beyond the webinars by joining her in the Future of Sustainable Fuels LinkedIn group that we established for you to engage with us as we lead up to the webinars and post webinars, and I'll explain that in just a second a little bit more. The first two webinars, Anchoring Themes and Coupling the Electric Power and Transportation Sectors, took place over the last couple of months. If you missed those, you can watch the recordings at the Lightspeed Solutions website, lightspeedsolutions.org. Today's session is the third, as I mentioned, and then we wrap this up looking at metrics, the challenges and opportunities in designing good metrics. So we have a webinar series and also a LinkedIn group put together is our forum. And I encourage you to go to the Future of Sustainable Transportation Fuels group and engage with other interested stakeholders, with Ellen and others from ASU, and also panelists and researchers from other organizations that are engaged in the sustainable fuels dialogue and research and development programs. I'm especially grateful to our promotion partners that help get the word out, the Environmental Law Institute, Commercial Aviation Alternative Fuels Initiative, Solar Fuels Institute, Solar Energy Research Center, American Council on Renewable Energy, National Association of State Energy Officials, Association of State Energy Research Technology Transfer Institutes, that's a mouthful, Frontiers in Energy, and the Center for Negative Carbon Emissions. This is how this is going to work with me first introducing Tom Seeger, and then I'll move into the agenda. But Tom is a scientist and engineer in the School of Sustainable Engineering at Arizona State University. He really focuses on environmental decision-making, life cycle environmental analysis, and impacts. Tom did he was an excellent panelist on a webinar we did recently as part of our Urban Resilience series. It was the first one in the series, and if you go to the SSF website into that series, look at the first webinar in the series, go to about minute 20 or 21. He makes an extremely compelling argument for how to approach the built environment and infrastructure there. Tom is really one of the most incisive thinkers that I've worked with, and I'm really pleased that he's able to moderate this session. Here's how this is going to work. Tom is going to do a very brief introduction to the series. He's going to introduce the panelists. Then we're going to move through each of the three panelists, have a short, about a 10 or 12 minute presentation. We have some predetermined panel discussion questions. Hopefully we'll maybe get a few arguments in there. That always makes it nice. We'll move into audience questions and then some final statements from the panelists. I ask that you take the brief exit survey at the end. That helps us improve our performance on the webinars. And we also ask that if you have some good ideas for sessions, please add them in there. And with that, Tom, I'm turning it over to you.
Thanks. I think Ed gave us a little bit of a glimpse of what this is going to look like. We're fortunate to have the three experts who are working in the area of recycling, closing the industrial carbon loop, that is, taking the CO2 emissions and recreating the transportation fuels that created CO2 emissions in the first place. But the purpose of the webinar is not to take what the experts know and to try and disseminate it to this community. The purpose of the webinar is to create new knowledge, and new knowledge will be created through conversations. We're looking for the conversations that aren't taking place in other forums. We want to catalyze them here. So we're going to ask our experts to speak. Then we've created a set of discussion questions that we want the experts to speak to, and then finally we want to bring the audience into the conversation. The audience members who are listening now can type their questions into the question screen. I will be looking through those questions as they show up, and I'll be selecting the ones that I think are most provocative to put to our panel towards the end of our webinar. And I hope that kind of format will engage you all as our audience. If we could go to the next screen. After the webinar, you will have the LinkedIn forum to continue these conversations, and hopefully it's out of those provocations that we get new ideas and we're able to accelerate innovation. The problem that we're working on today is one of the critical challenges that the Industrial Revolution has left us with. We have a huge open CO2 problem. Most of the people in our audience are familiar with the way material cycles work and the fact that our economy has perturbed those material cycles to the detriment of our environment. The combination of CO2 and transportation fuels, closing that loop would solve a serious environmental question as well as a resource that is a finite resource issue. So this is a critical question to sustainability, and it's why we've selected it for our webinar. To get us going, I want to introduce you to Claus and to Tim and to Jim. We're going to take our speakers in that order. You're able to read about them in the next slide, and so I don't want to belabor their bios as much as just to say that I'm very fortunate to be learning from the three of them today. Claus, your slides are queued up first. Will you get us started?
Thank you. It's a great pleasure to be here and be able to talk about the issue of closing the carbon cycle and making liquid fuels again. I would like to emphasize that this only makes sense in the context of wanting to close the carbon cycle. I do believe that particularly in form of ugly coal, but also in oil and gas, we have such large amounts of fossil carbon in the ground that it's very hard to believe that we can compete with those unless we have the problem of climate change, where we actually have to figure out how to balance the carbon budget. And while often this is stated as we have to reduce emissions, let me make one point very clear. If you want to stabilize the carbon dioxide in the atmosphere at some level, and it doesn't really matter all that much which level, you end up having to stop emissions virtually completely. So this graph I'm showing you here gives various scenarios where we, starting in 2010, follow various trajectories. The first one is we just have continued exponential growth as we have seen before. And long before the century is out, we escape from this little graphics at 800 ppm. If we held emissions constant, the CO2 would keep rising and rising anyhow, slightly sublinear because the ocean is picking up some of the CO2. This is a simple model which captures that, but we breach the 450 ppm level just a little later. Even at 1/3 of current emissions, the CO2 goes up. Even at 10% of current emissions, at about the year 2200, it turns around and comes up again. And even if we stopped completely, it would take a very, very long time to level things out. If we had an allowance of 1/3 of current emissions, the average person in the world would get 4% of the actual emission in the US. So for all practical purposes, we have to stop emitting, and we have to do it relatively fast. So in the end, what this means is that for every ton of carbon we take out of the ground, another ton must be returned. But there is a corollary to that, which is even more important. For every ton of carbon dioxide we put in the air, we have to take it back out, even if that is made from synthetic fuels, which were made without the help of fossil carbon. In the end, if we put it in the air, we have to take it out. And until we do something, the CO2 in the atmosphere will rise. And to give you a feeling for how tight we are, if every person on the planet puts out roughly 30 tons of carbon, which we here in the US do in about 5 years or 5-6 years, that would lead us to 450 ppm in the air. This is a permanent allotment. This is in perpetuity. This is not an annual allowance. So basically, If you burn through a tanker truck full of oil of that about size for every person on the planet, we have blown up our budget and we are past 450. And in order to stop, we have to stop fast. If you simply said the world will reduce carbon intensity every year by X%, then we would asymptote out to a finite level, but if we wanted to stop at 450 ppm, we would have to reduce carbon intensity by 7.3% every year, and I'm afraid that's already not practical anymore. So quite likely, we will have to fight negative emissions sometime in the future. So what we need to do is eliminate all emissions from all point sources. That mainly addresses electricity generation, but there's also steel, there is cement, and issues like that which have to be looked at. An important point is if you do capture and storage of that CO2, you can reach maybe 90% capture, and at a coal plant that means from a life cycle perspective you reduced emissions by about 75%. You didn't even satisfy the need that coal plant has to deal with its own emissions. Ultimately, and this is where the fuel angle comes in, we need to reach net zero emissions from distributed sources. So either we abandon fossil fuels, or if we cannot because they're extremely valuable in aviation, ships, and also in road vehicles, we have to figure out how to close the carbon cycle by making synthetic fuels, letting the CO2 out, and taking it back later. Ultimately, we may have to deal with overshoot emissions, and if we had to take 100 ppm back, we would be talking about 1,500 gigatons. So from my perspective, that alone guarantees that the cost of carbon storage will stay high in the future, because we will have to deal with past sins and overshoots, and that will take us a long time and effort. And during that time, it's very, very hard to make an excuse and say we are also burying new carbon. And I think this is the biggest argument why liquid fuels produced without fossil carbon are the ultimate approach to this problem. I would argue that ultimately that CO2 must come from the air. That could be a biomass cycle. If you grow crops and you grow algae or make algae-based fuels, that CO2 came via photosynthesis directly from the air, certainly if it's open field agriculture. But if your bioreactors are closed, then you rely in effect on technical air capture. You could run direct thermochemical or electrochemical fuel cycles, but I leave this to the next speakers. And ultimately, you can utilize fossil CO2 from point sources, but that can only be a stepping stone towards zero emissions, because if you think about it for a moment, this is still carbon which came from the ground, and yes, it has been used twice. So either the electricity is dirty or the fuel is dirty, but you cannot clean up both by doing this. So ultimately, sort of the dream is the new biomass where you have, let's say, photovoltaic or thermochemical approaches, and you rely on CO2 that came from the atmosphere and ultimately water, which came ultimately from the ocean, and you combine them in a chemical process where you release oxygen, and you now have energetic fuel, which at some later point you combust again and you put the water and the CO2 back into the environment. So much here hinges on the fact that air capture is feasible and affordable, and of course this is a big question. And people have argued that it's not, and they have cited Sherwood's rule, which suggests that costs of separation technologies tend to scale linearly in dilution, and unfortunately the CO2 in the air at 400 parts per million is quite dilute. Furthermore, to make the thing harder, the air has about 10 to 100 times as much water as it has CO2, and it turns out most approaches to collecting CO2 will also collect water. And while you could afford $30 or $50 per ton of CO2, you certainly cannot afford collecting even more water at that price. First-of-a-kind apparatus is always expensive. The American Physical Society recently, a few years ago, 5 years ago, suggested it could cost $600 a ton. I'm actually optimistic on that number because it basically says that you can start from a number which is not more than 100 times as much. And if you look at photovoltaics, that price came down by 100 times. Our own approach is to have a very interesting sorbent which has the feature when it is dry, it really likes CO2, it binds CO2, and as you make it wet, it releases it again. The graph here shows that the pressure of CO2 in equilibrium over this material increases roughly 500-fold. from having it outside in a dry environment to putting it into a chamber where it can be made wet. So that alone is a way of driving CO2 concentration up roughly 500 folds, and for us this is the first stepping stone to get to pure CO2 extracted from the environment. The strategy for cost reductions are to use passive collectors to avoid Sherwood's rule. We have shown that the linear relationship is typically the first contacting step. Uranium from seawater is a great proof that shows that it doesn't have to be like that. So therefore we design passive collectors. We just stand in at the wind like a windmill. We mesh the sorbent material to the problem. This was the moisture swing I just introduced. And ultimately, we plan to harness the cost reductions from mass productions. Many learning curves, photovoltaics is a good example, have gained factors of 100, and therefore we believe that is ultimately possible. So we take advantages of the resources in the air, and we use industrial processes of mass manufacturing to drive the cost of these systems ultimately down. You need to, lastly, you can integrate this with the power grid, because as we abandon fossil fuels in the electricity sector, we are confronted with intermittent renewable energy, and that needs time-flexible consumers, and it needs storage to shift energy for days, for weeks, and sometimes for months. Think about the difference between summer and winter and the availability of solar energy or wind. Liquid fuels, on the other hand, need very cheap power. If you pay 2 cents per kilowatt hour and you're 50% efficient, you add $1.60 to the gallon of gasoline simply to buy that electricity. On the other hand, if you pay $100 per ton of CO2 from air capture, that only adds 85 cents to the gallon. So ultimately, it's the price of the electricity which will make this difficult. But fuel production can take advantage of price fluctuations. If you have oversupply of electricity, you can do it, and therefore you use the time-flexible demand to balance the load. The ease of storage ultimately allows liquid fuels to provide backup power. You can sit on a gallon of gasoline or a huge tanker full of gasoline literally for a year, and you can supply fuels in the winter if your solar energy is not working as well as it did in the summer. So in conclusion, I would argue the need for collecting CO2 from the atmosphere will drive us to liquid fuels which are made synthetically, and that can have the additional benefit that it can solve the storage problem for power grids which are themselves not fossil fuels. And I conclude on that. Thank you very much.
Hi, this is Tom again. Klaus, the takeaway from your presentation is that closing the industrial carbon cycle is demanded by response to climate change. And you listed several methods by which we could recombine the CO2 in the water to produce liquid fuels. I think you were most optimistic about the thermochemical route. But our next speaker is going to talk about what you introduced, Klaus, the bio-based route, and show us how biology can provide an alternative to thermochemical closure. Tim, will you take it away?
Absolutely. Thank you very much for the opportunity to speak to everybody today. I'm with Alginol Biotechnology, and we've been very focused on developing a photosynthetic approach to the beneficial reutilization of carbon dioxide. And as many of you know, and as this slide presents, photosynthesis is one of our planet's best recycler of carbon dioxide. Nearly 260 billion tons of CO2 every year is recycled through photosynthesis. And so our thesis, when we developed the technology many years ago, or at least researched the technology many years ago, was that using the biological systems that have been in the business of using photosynthesis and consuming CO2 to regenerate and to develop ethanol and crude oil molecules via that process was an approach to beneficially reutilizing carbon dioxide and recycling that CO2 in the form of renewable fuels. And so over the past 8 years, our business has been focused on developing this technology and developing these pathways that beneficially reutilize the carbon dioxide in the atmosphere. And so this is just a quick shot of the technology approach that we have taken. Significant engineering and biotechnology has gone into the development of this technology, and we have focused in each area of this pathway and have really developed technology to both leverage the biology within cyanobacteria that has the ability to do the photosynthesis, as I mentioned previously, and then also produce a ethanol from that ethanogenic strain that we've developed over the past 8 years. And then in order to actually do that in a commercial fashion, in parallel, we had to develop technology that created the most efficient method for photosynthesis to occur in the cell. And we've developed these reactors, these photobioreactors, that allow us to take anthropogenic forms of CO2 and feed it to algae in a closed bioreactor. And then these systems have resulted in us developing a very efficient mechanism to feed and then also cultivate our algae in a commercial fashion. And then, of course, once you've produced ethanol and waste biomass from that process, you have to concentrate the ethanol, and you need to do it in a very low energy fashion. And so along the way, we have taken technology from the ethanol industry and leveraged that for our systems, but we've also had to develop low energy systems to concentrate the CO2 at low concentrations that we receive at very low concentrations. And of course, we leverage the process called hydrothermal liquefaction, HTL, to convert our waste biomass to a hydrocarbon and then convert that to a crude oil-like material that can be refined in a typical refinery. And that is all to say that how do you do this in a manner that allows you to have all the energy into a system that leverages photosynthesis and those photons that hit the earth and the alginol and the algae consume CO2 in the process. And so we've had to really take a very detailed look, because in the fuels business, the renewable fuel standard, especially for renewable fuels, is really the important public policy element that is really the guiding light for our business. And so through that process, the Environmental Protection Agency has evaluated alginol-specific pathway and determined that our process results in a fuel that is about 69% less carbon intense than gasoline. Other independent reviews by several universities have looked at our pathway as well and have indicated that the carbon intensity is potentially as great as 85% reduction. There are a number of companies in the algae space as well as other industrial gas space that are taking advantage of anthropogenic forms of carbon dioxide, and some in the industry are making biofertilizers, and they are leveraging the carbon benefit of often offsetting the man-made fertilizers with a biofertilizer and the fertilizer that consumes CO2 and actually consume nitrogen out of the atmosphere and depositing that nitrogen back into the soil. Others are reducing industrial processes, industrial CO2 processes by producing bioplastics. And a fair number of people continue to focus on chemicals as well as fuels in the space. And I think it's interesting to note that the President's Clean Power Plant rule is of very great interest to those who are in the business of taking any sort of greenhouse gas at this point and turning those into valuable commodities, at the same time offsetting or displacing the old forms of carbon in the form of crude oil, as well as reducing emissions from power plants. And I think it's important to note that the initial draft of the President's rules, 111B and D, which is the sections of the Clean Air Act that are pertinent to our discussions, did not contemplate the use of carbon utilization as a technology or a measure to reduce carbon emissions. And it wasn't until very recently that that issue has really been evaluated firsthand by government officials and other policymakers, and it's important. It's an important component as far as I am concerned in terms of reducing carbon emissions over the long haul, because we're going to be needing energy-dense fuels into the very long future for some time. And if you look at the mass balance of hydrocarbons on the planet to biomass, you quickly come to the conclusion that, oh my goodness, we need a lot of energy. And as the world continues to grow, in particular China and India and other parts of the world, you see on a worldwide basis that the demand for crude oil and dense hydrocarbon fuels continues to grow out into the future for some very long time, at least until there's a viable, economically viable and scalable solution to replace those fuels with. Senator mentioned Manchin from West Virginia, obviously a person very interested in coal production, but nonetheless also the utilization of carbon sponsored legislation this year that as part of the omnibus was announced this last week, that is now part of the omnibus energy bill that members of the United States Senate are now contemplating, and expanding the role of the fossil energy division from 7 to 8 priorities to include carbon utilization. You can see the language that the United States Senate inserted into the preamble of Title 42 of the Fossil Energy Code. And that enables this department for the first time, the Department of Energy, to actually look at other technologies beyond carbon capture and sequestration, like carbon utilization, as a method or one of the portfolios, one of the items or technologies in the portfolio that allows these technologies to be leveraged and utilized in an industrial fashion. So we look forward to working with the Department of Energy on that. The technology, at least on the algae side of the equation, is moving along in terms of its maturity. It's being demonstrated by my company in Florida and others, as well as, and there are even some implementations where companies have integrated their technology with flue gas systems, including this facility here in Kauai. And this facility, as you can see, is an open pond technology where they are taking flue gas emissions from this oil-powered steam injection combustion turbine power plant, and they're producing algae. In particular, they're producing a renewable form of biomass that is used in protein production. Other implementations of the technologies are interesting, and this plant, bioprocess algae, is actually integrated into a ethanol factory in Shenandoah, Iowa. And it's taking the pure CO2 stream, slipstream, from the ethanol production and feeding it to algae in this very large bioreactor. And again, they are producing a high-value product from that technology. This technology has been up and running now for several years and is moving through that development scale. A number of companies in the space have done offtake agreements with various refiners, including my company, with Reliance, which operates one of the very largest refineries in the world in Jamnagar, India. And there are a number of global partnerships that are beginning to come to bear with large oil companies as well as food producers. And again, this is all about the beneficial reutilization of carbon dioxide, taking carbon dioxide that would be otherwise emitted into the atmosphere, repurposing it, recycling it, in some cases sequestering it, but in most cases displacing the use of additional fossil fuel needs from fossil sources. And then if you look at the overall GHG reduction curve, I see this slide seems to be a little bit infected with the Mac to Microsoft disease. But essentially, in the business model approach that we are taking, we actually want to purchase CO2 from large industrial emitters, and that's the yellow alginol CO2 utilization. So you can see it's below the line. We're actually paying $1 a ton for CO2 today. We have signed 2 long-term 24-year agreements to do that. There is demand in the space for that new business model, and so we have a contract in place for 24 years at this stage with 2 very large utilities in the state of Florida. This graph just illustrates that there are a number of strategies out there for reducing emissions from and that carbon capture sequestration, albeit a technology that scales at the gigaton scale, really has a challenge because of its cost impacts associated with carbon capture sequestration. And I guess the point is that when you think about this in a portfolio, from a portfolio standpoint, the combination of both carbon capture and utilization might be the way of the future for the utilization of carbon dioxide or the reduction of emissions. And I think I'll finish on this slide, which is essentially we have been scaling up the engineering and science of this technology for many years, and we continue to be in the development phase, including the development of a very large processing facility in southern Florida with a very large power producer in the future. Thank you very much.
Hi, this is Tom again. Tim, thanks. You've presented for us the financial numbers that make a compelling argument that using photosynthesis, the way that nature closes the carbon cycle, is a viable business proposition for closing the industrial carbon cycle too. Our final speaker, Jim, is going to talk more about the thermochemistry, that is the thermochemical closure of the cycle that Claus was recommending in the first briefing. Thanks, Jim. Take it away. Jim, you might be muted.
Yeah, somebody, am I on now?
You are back now, Jim. Thanks.
I'm back. Yeah, somebody muted me on the dashboard there, so I was double muted. I appreciate the opportunity to speak to this audience, and I'm talking about a technology and an approach that has a little bit. It's a little different than what a lot of us are familiar with, so I appreciate the chance to talk about it. As Claus was saying earlier, what we really need to do is close the cycle around CO2 and around transportation fuels. And we believe that that's actually very important to do because it's going to be very, very hard to displace liquid hydrocarbon fuels. Certainly, there are moves towards vehicle electrification. There are moves towards the hydrogen economy. But there are certain applications, for example, air travel, heavy equipment, that you really just can't do better than hydrocarbons just because the energy density and ease of fueling with those things. So what we would like to do is, again, recycle, close this cycle. It's very similar, actually, to what the hydrogen economy looks like, which is another way to sort of close the cycle. If you were able to just remove CO2 entirely or CO2 entirely from the fuel stream, you could essentially split water, make hydrogen, burn hydrogen, make water, and you could go around and around in a loop as we see over here on the left. If we introduce CO2 into that loop, it looks more like this. We put CO2 in water. Somehow we put energy input into that. For example, in the biomass example we just heard about, it's sunlight. In my example that you'll see in a minute, it's also sunlight. We re-energize that. Now we have fuel. We expel oxygen. And then you can combust that and recreate the CO2 and water. So basically what I'm talking about is processes that are, there's multiple ways to look at it. You can look at it as reversing combustion. You can look at it as a chemical analogy to what biomass is doing, what photosynthesis is doing. But we're trying to make that more efficient, more on of an industrial type process. The way we're going to do that, we think one of the best ways to do that is just capitalize on chemistry that's been around for a very long time. This is syngas chemistry, essentially the reaction of carbon monoxide and hydrogen to make long-chain hydrocarbons, which can then be converted into gasoline or diesel fuel. Okay, let's see, here we go. Why are we interested in fuels? There's been a lot of interest in CO2 utilization for many, many years. As you can see over on the left-hand side of this plot, or this graph, is a very nice graphic back from 1998. And there actually are a lot of different chemical pathways that you can implement with CO2, a lot of very elegant chemistry, and people have spent a lot of time on finding useful ways to use CO2. But the disconnect is this, is that if you look at what the major industrial chemicals are in the world, this is broken down actually just by the United States. The three largest industrial chemicals by a long way are ethylene, propylene, and ethylene chloride. These are all polymer precursors. And so if you were able, these are numbers from 2004, if you were able essentially to make all of these chemicals out of CO2, just essentially on a carbon-for-carbon basis, so if I was going to make ethylene, I would need 2 molecules of carbon dioxide. You can add up all the carbon dioxide that you would need to make these 3 major chemicals. That number is here, about 139,000 metric tons. And then you compare that to the size of CO2 that we're putting into the atmosphere from petroleum, and it's only about 5.7%. And so I could make every milk bottle, every plastic knife, fork, and spoon, every piece of PVC pipe out of CO2 and barely impact the problem. If you start looking at coal and natural gas plus petroleum, it's even a more disturbing picture. You could only use about 2.5%. So we need to find something which is commensurate with the CO2 production. Essentially, fuel is where it comes from. Fuel is where it needs to go back to. So if you look at this, you look at it from a problem, from a standpoint of resources and costs, and you ask yourself, can I really do this? How crazy am I? We've looked at this, as have other people, and I've come to the conclusion and believe that it's certainly plausible that we could do this under certain circumstances. And then the primary consideration, or the primary metric that you have to meet, is a very high life cycle efficiency. I believe that you have to go from solar energy to a liquid hydrocarbon fuel with at least 10% overall efficiency, and that's on a life cycle basis. Very quickly, the reason for that is things just get very large. Solar energy is nice, but it's actually a very diffuse resource, whereas hydrocarbons are very energy dense. And so, for example, if you just look at the size of area that you would need using very generous assumptions on what the sunlight resource looks like, if I only did it at 3% efficiency, I would need the state of Georgia to provide U.S. petroleum consumption at about 20 million barrels a day. Actually, this is a dated figure. It's come down a little bit from that. But the idea stands, is that I need to drive the efficiency up to drive the size and scale down. Also, one can look at it as from a cost impact. Essentially, sunlight falls on a certain area, and I can think of it in terms of how much can I spend to collect sunlight per square meter. And so that's what we've done over here on the right-hand side. So this is a nominal capital expenditure. Again, some very favorable loan terms paid out over 30 years. And I can look and I say, well, if I spend $10 per square meter on my equipment, and I go up to a certain line here. Let's say this is 0.1% efficiency. Just the contribution of paying for the capital cost me over $10 per gallon gasoline equivalent. And so if you look at sort of more realistic, say, well, I want $5 a gallon gasoline efficiency. I come over here to 1% efficiency. At 1% efficiency, I can only afford about $60 per meter squared, which sounds like a lot until you consider that a very simple facility, something like a greenhouse facility that people put together for growing tomatoes in the South or in other agricultural areas, essentially you can budget that at about $80 per square meter. And so this, if it's going to cost $60, it has to be a very, very novel, very, very inexpensive process. So again, this drives us out towards these higher efficiencies so that I can push the price up that I can afford up to hundreds of dollars per square meter where actually what actual solar equipment costs. If we look at the CO2 and water, I think Claus has talked about the CO2. These are not a limiting resource. In fact, it's very abundant, assuming that you can collect it. Water is actually, the consumption is relatively low in this. It's about a gallon of water per gallon of gasoline in a stoichiometric point of view, more to account for some of the other uses that you will need. But again, it's a high impact opportunity for CO2. On the short term, we could look at stationary sources, but of course over the long term we need to implement technologies such as Claus was talking about. And what's the time frame for this? I would argue that to scale up to these types of things, it is certainly doable, and we have done it before. For example, the auto industry is about the size of an industry that could do this, but it would take probably decades to scale up to that size. Okay, very quickly, just what is thermochemistry? I think everyone's probably familiar with the idea of electrolysis. In electrolysis, we take essentially electrons, we take a potential, and we use that to split water. Well, it turns out you can also split water with heat and avoid having to, for example, turn heat into electricity. That gives you the chance, opportunity for greater energy savings, greater efficiency. Now the problem is that if you just heat water up to 4,000 degrees C and you split it, now I've got hydrogen and oxygen mixed together at 4,000 degrees C, and that's not very helpful. So what you do instead is you divide that into two separate reactions. For example, shown here, this is a sort of a conceptual version of it. You can think of this as an iron oxide, for example. If I heat it up with a concentrated solar flux, I can evolve oxygen. I pull that oxygen away. If I cool the temperature down in a thermodynamic sense, now it wants to be reoxidized. And so if I introduce steam or CO2 at this point, it will reoxidize those materials and produce carbon monoxide and or hydrogen. And so essentially, now I've regenerated the metal oxide, which I can cycle around and around and around. And so sort of a convenient way to think of this is that it's actually an engine in which I'm inputting heat from, in this case, from concentrated solar energy, and my product out instead of mechanical work is chemical work in the form of energized CO2 or energized CO and hydrogen. The catch is, one of the catches is there's a lot of subtleties to how you do this efficiency. One example is that the thermodynamics require you to do the reactions at two different temperatures. And so managing the sensible heat that's built up in these oxides, I have to heat them up to a high temperature. I put energy in to drive the reaction. Then I have to cool them back down. I have to somehow figure out how to use this temperature or this heat that I've stored in the material as I cool it down to reheat this back up, or I pay a big efficiency penalty. And then in the oxidation reaction, there's a small exotherm, but some of the energy goes to produce fuel. So there's a lot of other details here that I'm going to skip over, but there's a lot of subtleties to actually how you make this efficient. Moving on. Now, we have looked at this. This is not just some laboratory type idea. We have looked at this, demonstrating it on sun, as have others. Our first-of-a-kind approach was to try to build in thermal recuperation between these two steps, as I mentioned. Essentially, we have in this device we call the counter-rotating ring receiver reactor recuperator, or CR5. This actually describes how it works. We have concentrated solar flux enters an aperture. There are a series of rings aligned on an axis, and each ring moves countercurrently to its two nearest neighbors, as you can see here. In the hot zone, these evolve oxygen. Oxygen is pulled off, and then a hot ring rotates this way. As a cool ring, its neighbor is rotating this way. They can exchange heat through radiative heat transfer. Now they're in a cool zone where we introduce CO2 and collect CO. And so the reactorizing recuperator is really the idea here. And again, this is an actual device. This is what it looks like on its test stand. This is an
Jim,
example
we only have a few minutes left.
Okay, I'm wrapping
it
up.
You have a
right.
take-home point slide.
Yep, I'm wrapping it up. So this is an example of the data that we've collected. You can see that we have a reduction temperature of 1500, an oxidation of 1100, and we were able to produce significant amounts of carbon monoxide. So to wrap it up, I believe this is my take-home slide. So again, I think that my main message is that solar fuels are plausible. They can make a huge impact, but we need to look at concepts that have very high efficiency, and that includes throughout the life cycle the embedded energy costs of the materials and so on. I think one reason for that is that it's often unappreciated that sunlight is actually a high-cost feedstock, and that's because we have to pay the capital cost of the equipment to collect it. CO2 and water aren't limiting. There's a lot of issues with low efficiencies in terms of scale, which challenge our resources and the cost. Thermochemical is a particular approach that I'm interested in. It's a relatively small global community out there, but we have made significant advances. Sunlight to hydrogen efficiencies of 3 to 5% have been reported, even amongst just this relatively new and small group. And in order to move this forward, you know, it is a relatively immature materials, reactor systems. They all impact efficiency, and these are all areas that we need to study to move forward. But we have some help in that regard, in that it's adjacent to solar electric, it's adjacent to solar reforming, it's adjacent to other technologies that are currently being implemented, and we can take advantage of that to move us forward. And I believe that's all I have for today.
What we've done so far is we've got the why, that is the imperative from Claus, and we've had two technical descriptions, a biopathway and a thermochemical pathway from our experts to say what are the technologies that would allow us to meet the challenge of this imperative. These are pretty much the conversations that are taking place right now, at least in the academic and expert communities. On our next slide, we have an example of discussion prompts that will help us go to conversations that aren't taking place yet. And this is where I hope we get a lot more audience participation. I want to ask the panelists to start with question one. And here these questions are intended to be provocative. They won't lead to answers, but hopefully they'll lead to new ideas. And if you wouldn't mind, Claus, coming back into the conversation here and addressing the question of whether recycling fossil fuel from stationary sources would impede the transition away from fossil carbons. That is, some skeptics want a more radical approach that says we should be eliminating the hydrocarbon fuels from the economy altogether. What's your viewpoint?
Well, I am sitting a little bit on the fence on this particular issue. If you look at it straightforwardly, what I said, I actually added a technology too, not just the imperative, by saying ultimately you have to close the carbon cycle by getting the CO2 from the air, and I proposed one particular form of pulling CO2 out of the air.
Thanks for reminding me of that. Yeah.
I think in the long run, it's impossible to close your book by saying that CO2 from the coal plant, which by the way is now more because it had to capture it, is simply being used and then put into the atmosphere. So in that sense, it's a non-starter. And I think in some ways it's actually detrimental because it entrenches a technology you don't particularly want to entrench. On the other hand, all the other technologies have to learn, and this is cheap CO2. So you have that back and forth. I think if you put a carbon price on carbon, ultimately, these coal plants will go away. And keep in mind, they cannot clean up if they give the CO2 to you. They give you fossil carbon. So your fuel is either fossil carbon or the power plant was still an emitter. You can't have it both ways. And so I think it has to go away in the long term.
But Klaus, couldn't we just eliminate coal-fired power plants altogether?
And then where did your CO2 come
from? There's still plenty of CO2 in the atmosphere that needs to be removed to get us down to, or at least I was going to say to 350 or other goals.
You will have the CO2 in the atmosphere which you just combusted. So the fuel cycle, once it's closed, is net neutral on the carbon dioxide content in the atmosphere. The amount you want to come down, if you want to go to 350 ppm, you cannot make fuel. You have to do carbon capture and storage. You have to dispose of that excess CO2.
Yep.
And my view is you could, in principle, do this with a fuel. You burn petroleum and you bury the CO2. The reason I am so interested in fuel production is twofold. One is the price of storage will stay high if we have to figure out where to put 1,500 gigatons of CO2, and that's what we will have to do if we reduce CO2 by 100 ppm. The second part is if we go to intermittent power sources, we better have a way of bridging the gap and have a storage system. And on the longer time scales, if we are not thinking hours and minutes, but days and weeks and months, they're the by far best way of storing the energy you don't need right now and want to have later is to store it as liquid fuel, which you then can branch a large fraction of into the transportation sector.
Jim, what about your reaction to this idea that if your technology is successful, you're just enabling a fossil fuel economy?
Well, obviously, I'm not a believer in that point of view, or I wouldn't be focused on the business. And the reason I'm not is because from a practical standpoint, there is going to be large amounts of CO2 produced from industrial sources out into the next several centuries. And just from a practical economic standpoint, many countries that are in the process of industrializing are going to continue to do that. And I know that there are some good news on the horizon, that there are some reductions coming in some nations like China. But the practical fact is that we're going to continue to use and burn hydrocarbons. And so the best way is to support the reduction of the intensity of carbon dioxide, much like the approach that the state of California has taken in the low carbon fuel standard, to reduce the overall impact that these dense hydrocarbon fuels have had or are having or in the future will have on climate. And so the point is that you're going to continue to need to reduce the carbon intensity of electricity production and all energy production. And one of the ways to do that is to reduce the carbon intensity of fuels. And then finally, even with air capture, we would be very satisfied in receiving that concentrated form of CO2 with air capture. It doesn't eliminate our technology. It actually expands our ability to do what we want to do, which is reduce emissions.
Right, and I disagree with you on one point. If you had said this is a bridging technology for a decade or two, I would say, yes, you are reducing CO2 emissions. If your plan, though, is to say, well, for the next century, we are going to see a lot of CO2 from fossil carbon sources like power plants, you cannot have that CO2 because you ultimately put it into the air. So that CO2 must be stored because otherwise the power plant is not carbon neutral. and you cannot become, or you are not carbon neutral because you are burning fossil fuel, right? Because
yeah,
you're
I'm also displacing fossil fuel.
Right, and so
and on a life cycle basis, the data is very clear. I reduced carbon emissions of fuels by 69%.
I actually think this left out of the box the power plant itself.
So I'm not in the business. I'm not in the business of shutting down power plants, of course, but there are a number of technologies, whether it be storage or other uses of carbon dioxide, that are going to have to be part of a portfolio over the long haul in order to buy down the cost of storage.
You need to get rid of the fossil. Build the control box large enough. If carbon came out of the ground, it has to go back into the ground, and you put it ultimately in the air. Yes, you helped because you didn't use the petroleum you would have otherwise used, but the power plant made more CO2 than it made otherwise, and all of that CO2 ends up in the atmosphere.
No disagreement. I'm just saying we are part of a portfolio, because my thesis is that you're going to need dense hydrocarbon fuels for a very, very, very long time.
Oh, that we agree on, but I'm saying you need to have the air captured source. Ultimately, that CO2 you use had to come from the air in order to balance the books on the air.
No disagreement,
and I think later when we get to the audience questions too. Tim, I want to invite you into the conversation by asking you to respond to this discussion question 2 first. Here, there's some skepticism about the life cycle benefits of recycling fossil CO2. Can you comment on that?
Well, I mean,
yeah.
Go ahead.
Yeah, is it Tim or Jim?
I'm sorry, I meant to invite Tim here.
Oh, okay. All right, great.
So I guess the controversy is around the methodology, and I think the methodology is quite clear that it all depends on where you draw the box, of course, right? But based on the way we do measure the life cycle of carbon, and which has been substantiated in the academic community, is that energy inputs in minus the processing inputs to your process, as well as the overall reductions of emissions, either through displacement and the energy outputs, result in a reduction in carbon emissions. You know, it's fairly grade school level accounting of carbon in, carbon out that we're talking about. I don't know that there's a great deal of disagreement by those who are experts in the space of carbon accounting.
Right. I would, to add to that, I would say that essentially my understanding of the accounting is that essentially you're not, as Claus says, you're still putting it into the air, but you're changing the rate at which it enters the air. And so ultimately, to completely close the cycle, I think we're all in agreement that it has to come from air capture. But in the short term, as Claus was mentioning, technologies have to get CO2 from somewhere. All of these things have to grow up, and it's a convenient source of CO2. It's part of the learning curve, I would say. And as far as the life cycle emissions, again, this is why we were so one of the reasons that you have to be concerned about efficiency, because as you build up a very large industry, let's say, that includes glass, steel, concrete, all of these sorts of things have embedded energy. And in order to account for that, in order to make your overall system net carbon positive, you need to drive the efficiency to as high a point as possible. So yeah, if you're looking at very low efficiency processes, I would say the life cycle is maybe questionable, but that is one reason why you need to drive yourself to ever better and better processes.
Jim, you gave us some introduction to the technical challenges. How long is it going to take to mature these technologies to the point where they're technically and economically viable? Well,
they're two separate questions there. technically, we can make fuel from CO2 and water tomorrow. We could take, for example, a PV panel. We could split water. We can take the hydrogen, react it with CO2, and make methanol or syngas, which we could then make diesel fuel or gasoline. And we could do that tomorrow. So the technology exists. The question really, as Claus mentioned and showed in one of his view graphs, is the cost of electricity is what drives that. So if you look at, you know, the question of what is economic viability, then you have to look at what you're comparing yourself to, right? If you say, well, I'm comparing this technology where I'm going to take sunlight, I'm going to build a plant, and I'm going to collect water, and I'm going to collect CO2, and I'm going to try to make it cheaper than something I'm pumping out of the ground, that's extraordinarily, extraordinarily difficult. So as long as we're not paying the sort of the hidden cost of emitting CO2 into the environment, at least we're not paying it in terms of dollars and cents, that's a very difficult place to put yourself into from an economic point of view. Now, the reason we were looking beyond, say, PV and electrolysis is to try to drive the efficiencies up to even higher levels, which we believe will help us in terms of the scaling and also in terms of ultimately the economics. But from a technology point of view, just can you do it? I think the short answer is you could do it tomorrow. Could you make money off of it? In today's market, no. And so it depends on what your approach is. If you want to look at the thermochemical approach, it's, you know, we may be a decade or more away. If you want to look at scaling it to the size of today's petroleum industry, then you're looking at many decades away.
And Tim, I think you have a little bit different viewpoint. Same question. On the biopathway, what's the time frame that it would take to pursue that technology?
Yeah, so on the biology pathway, I'm just making sure I understand the question, which is what is the time frame to commercialization?
Mm-hmm.
It seems to me that we have spent a decade or so really with in the process of optimizing on the bio pathway. On the biotechnology side of the house versus typical biomass, it's grown as a crop. You know, we are now at the point where we can achieve commercial economics in our process. So really the balancing act that many companies at my state are in is that they are at the point where they are ready to commercialize, but the markets are capital poor. Where there is a lot of capital in the marketplace, the investors haven't bought into the idea that the policy elements that are really required for bringing any new technology to bear are stable enough for them to really have a fair shot at competing economically over the future. And it isn't that we can't produce low-priced fuels or competitively priced fuels, but in order to have a fair parity with the current set of incentives that are in place for fossil sources of energy, we need to have a system in place, whether it's a renewable fuel standard or low carbon fuel standard or other policy elements that provides parity with you know, older technology. And so really, we're at the point of time where we can begin to implement and commercialize. We're ready today, but we have to still continue to work on the policy elements so that there's parity in the marketplace and that the investment community feels that the stability is there so they can bring the resources to build these plants.
This leads us right to our fourth discussion question.
I can add a brief remark there.
Yes.
I would first of all strongly agree with the argument that we can electrolyze today. We can do Fischer-Tropsch and all of the syngas transformation. This is all old technology. The critical point is to have cheap electricity. But that you can't really get around. I do believe that on the air capture side, our goal is to demonstrate it on feeding it to algae and other low-grade CO2, which is just a few percent in the next few years. And I do believe that in less than a decade, you can demonstrate this, and ultimately it becomes cheaper. But you do need a policy framework which drives it, because coal, oil, and gas will always be able to undercut this.
Claus, you just mentioned, again, the importance of inexpensive electricity to the commercial viability of existing technologies. And that was something that Jim brought up too. And Jim, you mentioned that this is why you were looking at using thermal rather than electrical ways of splitting up CO2. Can you return to that and comment on that? Where are the policy drivers, how do the policy drivers impact your choice of technical pathway?
Well, the policy drivers, they impact no matter how you do it. Sort of, I think is the big picture there. Is that you need policy drivers that, as you've written on the view graph here, that incentivize or create barriers for CO2. You know, you either have to pay somebody to reuse it, or you have to put a barrier for somebody to put it into the atmosphere. And essentially, what you need to do is put a price on the carbon. Now, there's a lot of different ways to do that. In terms of the technology, if that price is not high enough, it drives you towards more and more efficient processes. Essentially, you need to, again, if we're going to compete with fossil energy, you need to bring the price down. And as Claus said, it's very easy for them right now to undercut almost anything we would do. And so the technology that we're looking at, again, is you know, we're looking at it because we think it may scale better as the efficiency gets higher. We think that that we may ultimately be able to bring the price down into a reasonable point, you know, where we can compete at the less than $10 a gallon basis. We've done some economic analysis that would indicate under favorable circumstances we could get down into $7 give or take per gallon gasoline equivalent, but that's not $3, which is what a lot of us are paying now. And so you need essentially a price for CO2, I believe, and you need you know, I guess if the price is too much, that will drive you towards inefficient processes. But if it's, you know, right where it needs to be, it will drive folks to better and better use of that CO2.
It really is the electricity, because if you were to put $100 on a ton of CO2, which is, in my view, a very high price, you would end up with paying 85 cents on the gallon of the gallon of gasoline, because that's what it translates to per gallon of gasoline. If you pay 2 cents a kilowatt hour, which is a very cheap price, which you only get in places like Iceland, you would end up paying $1.60 for the electricity per gallon of gas, assuming you got to 50% efficiency, which is also challenging. So it seems to me the central issue is the cost of the energy, whether it's brought in thermally or from electricity. And the point I was trying to make with the grid is we have a tendency to think that electricity is on the top of the totem pole and the most valuable form of energy. But if you make electricity at the wrong time of the day, when there is no consumer for it, it's worthless. And if you had a source of electricity which is operating at 6 cents, think as a windmill, and you can charge 10 cents half of the time, and you have to live with 2 cents for the other half of the time, you're still averaged out to where you wanted to be. So you can.
Right. So I would say this goes back to sort of the first question about the stationary sources, right? And so one reason that it's hard to imagine a future right now without some fossil energy contributing to the grid is because of the storage issue, right? Is that it tends, we have a disconnect between
but you have no choice. You have to store that CO2. You are not in the long run. Your emissions have to go to zero.
No, but okay, I accept that point. But the issue that the grid people are facing right now is that if I continue to put more and more renewable energy onto the grid, I produce it, as you say, at the wrong times. And so when everybody gets off from work and goes home at the end of the day and turns on their TVs and their air conditioners and whatever, there's not a particularly great solar source, right?
Right.
And so that backup is being provided by fossil. So as you say, this could provide some type of storage to shift that that production to a demand to meet the demand curve, if you will, right?
Yeah, but not only that, it's also a very flexible consumer. You can say when the demand in the grid goes up, my fuel production slows down. If the demand in the grid goes down, my fuel production goes up. And if you don't have enough electricity in the grid to make it work, then you have a liquid hydrocarbon plant which is converting some of that fuel you made back into electricity, but net total you're a fuel producer.
Right, and the downside of that is the round trip efficiency then gets actually pretty low, going all the way from electricity to hydrocarbon and back to electricity.
That may be 30%, but if you store in a battery and you pay the rent, the capital cost of that battery for 24 hours, you are at about 20 cents per kilowatt hour just for that.
I agree. I understand your point. Yeah, the cost of, we don't have other good alternatives right now.
And the efficiency is overrated because this was wasted electricity. You couldn't do anything with it. And if you can transfer 30% of this to later, keep in mind you paid 2 cents a kilowatt hour for it. So even coming back at only 1/3, that's only 6 cents per kilowatt hour, plus of course all the costs you had in storing it, right? But the electricity, the efficiency itself, I think is in this particular instance overrated. You are better off to have one means of doing it, and right now we call this the unsolved problem. Here is a solution. It's not all that hard.
I like that you're pointing out, Klaus, there is no one electricity price. Electricity moves up and down because the electricity demand is momentary. We can't smooth it out the way that we do for transportation fuels, for example.
Right.
But I also want to go a bit off script now. One of the questions from our audience was asking about the role of forests. And I'm going to enhance this question because it occurred to me too. When I look at the atmospheric concentration of CO2 data, for example, that which comes from Hawaii, and we see it on a weekly basis, we know that it has seasonal variations. Of course, it's going up, up, up in the way that you showed us, Klaus, in one of your first slides. But what impresses me is that when it is summertime in the northern hemisphere, the concentration of CO2 in the atmosphere actually goes down. And that's because the photosynthetic cycle, the natural carbon cycle, is about 30 times larger than our industrial carbon cycle. So we already have a mechanism for taking CO2 out of the atmosphere and using photosynthesis, combining it with water and creating hydrocarbons. That mechanism is principally our forests. Klaus, you haven't talked much about the role of deforestation or reforestation in, if not closing the industrial carbon cycle, at least managing the CO2 level in the atmosphere. And I'm wondering if you have a reaction to this question. What is the role of our forests?
The role of the forest, the problem is the intake and the outtake in a year is very, very high. The total capacity is not all that large. The standing living biomass is about 600 gigatons. To round up a little, we are putting out about 10 gigatons of carbon a year. So in 60 years, we would have to double all the forests in the world. And I think that's environmentally not feasible. So I see that as a As a player, I think I would be far more concerned about the environmental disaster we create by getting rid of forests, which should be there. As far as the CO2 problem goes, we didn't create the CO2 problem by cutting down forests, and we're not going to solve it by growing forests. It's just not enough capacity in that reservoir, although its ability to go in and out is very powerful, right? If you look at the rate, jumps to about 25 ppm per year in midsummer as it removes CO2 from the atmosphere. So it's a powerful tool that way, and one of the approaches people have suggested to control the CO2 in the system is to grow biomass, burn it in a power plant, and dispose of the CO2 in carbon capture and storage. This is known as BECCS. The problem I have with that, and this goes to a point Jim made, if you now ask how big are the forests you have to grow to do this, so you're overmatching the world's agricultural land. And we are entering into a phase where agricultural land is valuable because lots of countries have reached the point where their diets become more protein rich. And if you start eating cattle and beef and pork, as in China, you start quintupling the amount of land you need to provide the same amount of calories. So it seems to me competing head-on with agriculture is a disaster in the making, and the environmental impact, if you start controlling the growth on those large scales, is pretty phenomenal. Think of palm oil plantations, which are, of course, the economically smart way of doing this. So I'm a little skeptical of pushing biomass too hard, but in the short term and in certain locations, it certainly can contribute.
That skepticism presents a serious challenge to Tim. There are two questions from the audience related to your technology, Tim. One is, can you base it on the oceans? Because this relates back to the competition for land and agricultural land in particular. And the other one is, what are the environmental risks associated with large-scale algae production? I'm hoping, Tim, that you can respond to those skeptical questions and give us a little bit of your reaction.
Yeah, those are fair questions and good questions. And so first off, I don't know of an algae technology solution in play today that utilizes any fresh water. So first off, the utilization of salt water is a key part of everybody's technology in the space. So fresh water utilized for agricultural production as well as human and animal consumption is certainly, if you're in the business of producing energy, off the table. So everybody uses salt water. Second of all, almost everybody in the space is focused on non-arable land that is either no longer suitable for agricultural production or is currently not suitable for agricultural production. For example, inland or coastal deserts. For example, the state of Florida, where we have a small project, and we're using land that was once used for mining, and that reclaimed mining land has no more nutrients, and it's not suitable for agricultural production today, and so therefore we're leveraging the availability of that land. And of course, Florida has an abundance of salt water, being an island that floats on a big gravel pit and on the Atlantic and Gulf of Mexico. So we feel very comfortable on the sustainability aspects of the use of non-arable land and saline water or saltwater brackish water. As it relates to the environmental risks, I'm assuming associated with algae production, I would say that at this point in time, the EPA considers them minimal, and in fact, the state of Florida has issued us a regulatory pathway, essentially a statutory exemption to a very, very stringent set of rules associated with the production or the importation of new plants and materials into the state. And we've also received a biotechnology exemption from the EPA because it's been found that our biotechnology platform in the form of algae are not suitable for living outside the environment we create. So they have to live within a very narrow range of environmental attributes in order for them to survive. And so our algae the algae that we utilize simply don't survive out of the range of environmental conditions we provide for them.
There's a little bit of time left before we're done, and I want to give each of you a chance to kind of wrap up or summarize, especially if there's something that surprised you about the interaction or something that you feel like you learned that you're going to take away and think more about. And I'm going to ask you to go in the reverse order that we started, which is going to give you the last word, Klaus. Jim, do you have a kind of a wrap-up or a summary, or can you share with us your experience of the webinar in just a few minutes?
Sure. I think there are several things I'd like to touch on, and one is I think that there is no one solution. I think biomass has got to be a part. I think that fuels from sunlight have got to be a part. I think there are a lot of things that have to happen transition-wise to make this happen. Ultimately, though, I believe that we do have to capture CO2 from air, and that using that as a fuel and closing the cycle around that is a viable path forward, and quite frankly, may be the best path forward. As far as I think a lot of us, as far as the webinar, I think a lot of us are largely in agreement on the big points. Some of the details, perhaps, that we may differ on. But I think the takeaway message is that the price matters, and that is difficult because of the incentives and whatnot that are provided to fossil energy, and we need to do something to correct that. And the price in terms of looking at these solar type facilities is very much connected to the price of energy, which in my view of the world is connected essentially to the capital cost of collecting sunlight. So whether it's renewable energy in a sense is free, but capturing it and collecting it is the price that you actually pay. And so you need to use those dollars well. And that's a bit of a rambling discussion perhaps, but that's my takeaway points.
Tim, do you have a reaction to the webinar as a whole?
Well, I think it's important to note that we all agree on the big points, which is that closing the carbon cycle is absolutely essential. So the best scenario for me is to receive my CO2 from an air capture system. I reduced my carbon footprint dramatically, even lower than 69%. So point number one. Point number two, I'd say policy, in this case, policy really matters. And we have to get to a point where the playing field is level for the fuels and the energy systems that we are developing with traditional fossil sources of energy. The fact is that those industries have a very good deal. This year is the 100th anniversary of the United States system of tax incentives for oil and gas. 100 years of durable policy in place to encourage significant production and domestic production of energy from the oil and gas side. The last time, you've never seen 100 years of durable policy in the area of renewables, whether that's wind, solar, whether it's on the electron side or the molecule side of the business. And so we've got to get to a point where there is durable policy, and it does matter in making this transition, forcing this transition, leveraging this transition to a cleaner energy system. And then finally, I think there's going to have to be a realization by policymakers and consumers of energy that we simply are going to have to bite the bullet, and we're going to have to really make good energy choices. And I don't have an answer for how we do that, but there's going to be a lot of education that has to occur, and policymakers are just going to have to get with it and understand that there's going to be pain associated with that transition to a cleaner energy future. But there are technologies out there in the wings that are ready to come online and begin to help make the transition a little bit more economic.
Thanks, Tim. Klaus, will you help bring us home here?
I'll try. I think one of the things I'm learning in this discussion is how difficult it is to actually draw closed boxes. And I do believe that the negative emissions aspect I'm pursuing is actually ultimately important. And I've realized it in this discussion, how important, because you can ask, why do we do all of this? Why don't we just keep using petroleum and then use some way of air capture to go into carbon capture and storage? And I think it's ultimately the IPCC's view that we have to come back, that we will overshoot 450 ppm and we will have to withdraw 100 ppm, which then for me the conclusion is that in the long term, disposal of carbon dioxide will be very, very expensive because we are constantly trying to find new places to put it because we have unlimited demand for it, and that will keep prices up. And therefore, not emitting is a very powerful way to go, and closing the carbon cycle will do that. I would argue it's technically feasible right now, right here. We could do electrolysis. It could be done a lot better. In the process, we will learn a lot of things. I think algae are an excellent way of feeding CO2 back into fuel. I think thermochemical processes are very interesting. And all of those have their role to play in a niche. By the same token, my approach to capture from air is not the only one. We can look at other ones as well. And we have to find a system that balances everything off. I think in the end, what we really need to do, and that will also make clear where one should go, is to outlaw the emission of carbon dioxide, which comes back to saying if you dig up a ton of carbon out of the ground, another ton has to come back. And if you put a ton of CO2 into the air, another ton has to be taken out. That balance will ultimately drive where all of this will come out. And I think all of the bits and pieces we have here, plus additional technologies we haven't even imagined yet, will help make this work. I really liked your quote up front that our ability to solve a problem is ultimately limited by conception of what is feasible. So we should be a little daring and figure out what is feasible.
Well, for all three of you, thank you for spending your time with us and for expanding our imagination on what we can do to connect these two problems of transportation fuels and climate change. We are right on time, and I want to hand it back to Ed Salzberg, who's provided this platform for us so that he can tell the audience how they can access the archival record of this and about some of the new webinars that are coming up. Ed, are you ready to take over?
Yes, thank you, Tom, and thank you, Claus, Jim, and Tim for a really insightful session. Your expertise is really comes through, and you're just such valuable resources to this discussion. And Tom, you did a great job as a moderator. I'm gonna select you as my top choice for moderators this year. And thank you very much for stepping in and leading just a great discussion. I want to remind you that we have one more session coming up. We've tentatively scheduled for August 26th as we're trying to firm the panelists up. We'll have that registration open this week. I invite you to go to the Lightspeed Solutions website to see the videos of the previous sessions. You can also monitor our progress with this session as well, with the next session, I mean. And then finally, I invite you to the Future of Sustainable Transportation Fuels LinkedIn group. We have more questions than we were able to answer in this session. But if you join the group, you can bring those questions up within the group, and we'll be encouraging the panelists to join too, so that they can engage with you directly on those topics. Also, the slides are available right through the GoToWebinar window. If you look at your window, you'll see at the bottom that you do have the opportunity to download the slides directly here, and we'll have the video posted up on the Lightspeed Solutions site within a couple of days. Again, I want to thank the panelists and Tom for moderating this, and I especially thank the audience that signed up, came to this, and stayed with us right to the very end. So with that, thanks. I'm going to end the session.